Welcome to the Anamena video tutorial about concentrating solar power. This is unit number 7, block 6. This lecture is about utilization of Greenius for annual yield analysis of CSP plants. We will go through several exercises to demonstrate a typical workflow. My name is Jürgen Dersch and I own a diploma in mechanical engineering and also a PhD in mechanical engineering. I have more than 13 years of working experience as scientist and also project manager at DLR in the area of CSP. My main tasks are design and programming of CSP performance models, integration of CSP and fossil-fired power plants, design and layout of almost line-concentrating solar fields, feasibility studies and consulting services, and as well development and maintenance of the software Greenius. In order to learn how to use Greenius, we will start with a first exercise. This exercise shall be a 50 megawatt parabolic trough plant located in Aswan, Egypt. The latitude and longitude as well as altitude and time zone are given here. A meteorological file called Egypt Aswan is provided with the software. As collector type, you should use Eurotrough collectors with short heat collecting elements. For the solar field size, 4 collectors per loop and a total of 156 loops should be used. A 2-tank molten salt storage with 940 megawatt hours total capacity and 130 megawatt maximal charging and 112 megawatt maximal discharging power shall be used. As power block, the Greenius standard 50 megawatt power block should be used, and the operating mode shall be solar only and no fossil fuel shall be used. If we start the software tool Greenius, you will see an input field like this one. Greenius starts a wizard offering you several possibilities. In this case, we choose new project and are going to start a new project. The next step is we can give the project a name. In this case, we choose Anamena 1. Go to the next step. The next step offers us to select a technology. We want to simulate a trough power plant with storage. And the next step is to load a meteorological data file. In this case, we want to do a simulation for Aswan in Egypt, and this is the correct meta file. We open it, and Greenius gives us feedback that is loaded a couple of data sets for this input data and a total of 8,760 data sets. That means one data set for each hour. After this, Greenius gives us a warning that the meteorological data set shows a site which is not the same as the site coordinates given in the location form. In this case, we should accept the proposal of Greenius to copy the meteorological dataset coordinates to the location dataset. After this one, we have loaded all important figures and can finish the start wizard. If you look into the details and open the important forms, we have started to load with the Aswan Meteor Norm data file. This form gives an overview about the data loaded and also the coordinates, latitude, longitude, altitude, and the relevant time zone. You can inspect several input parameters like ambient temperature, pressure, humidity, or direct normal irradiance. There is one line for each day of the year and one column for each hour. The second thing we had done was to copy the coordinates of the meteor dataset to the location dataset. So here it's important that the latitude, longitude, and altitude and time zone information is the same as for the meteorological data file. If not, this may cause errors in the simulation because the sun may be below the horizon and the meteorological dataset offers direct normal irradiance and vice versa. So the Greenius software itself is organized like many other Windows software. We have a couple of menu entries called File, Load and Save Projects, to load previous projects, to set up preferences, and so on. Then with the project case, we can run the calculation, create a copy, or select a technology. We have a couple of different tools, for example, a shading editor. If we have several projects open, we can switch between the windows with the window menu entry, and we can choose a language. In this case, we have an English version and a German version. And there is, of course, an online help file available for Greenius. We switch now to the Technology tab and choose the collector which has been proposed. Using the Load button offers us a couple of different collectors. In this case, we will choose the Trough 2 with HCE. Open it and load it into the software. We can now inspect the data. Here, the collector dimensions are given, nominal optical efficiency, the heat loss coefficients, and also the incidence angle modifier coefficients. On the right-hand side, we have a graphical representation of the collector efficiency in this case, but we can also switch this to inspect the incident angle modifier, with included in the influence of cosine and excluded influence of cosine. So after loading the parabolic trough collector, we have to define how the solar field should be made up of these collectors. Again, in this case, we can load a prepared data file, or we can do all these changes manually. Here I have prepared one data file to save some time, but user is able to modify all these numbers. We have the number of collectors per row, it's 4. The number of rows in the solar field, it's 156. And from this and the aperture area of a single collector, the effective mirror area is calculated. Here plotted in gray, which means that the user cannot modify this value directly, but it can be modified by changing the number of rows in the field, for example. Further information given here is the distance between rows, distance between collectors, and header lengths, as well as header diameters and piping length in loops and diameters, as well as specific masses for these pipes and headers. The solar collector field has a second tab, which is called Field Operation. Here the nominal outlet and inlet temperatures are defined, as well as mean mirror cleanliness, the shutdown wind speed, and the type of heat transfer fluid. Further information given here is the piping loss coefficient, which is a specific heat loss based on the aperture area of the solar field. And also the expansion vessel losses. Expansion vessel losses means here all losses of expansion vessel and heat exchangers. Greenius offers also automatic calculation of fluid mass, but this can be switched off by the user and a known value for the total mass can be introduced. The thermal storage input field shows here a net capacity of 940 megawatt hours. The consumer design input is taken from the power block information. It's 129 megawatt. Also the full load hours is calculated from the net capacity divided by the consumer design input. The user has to define maximum charging and discharging power, which may be different since the same equipment is used. That means the same mass flow rate has to be used, but temperature differences are not the same. Another important information is about the relative losses in 24 hours. Here we have a value of about 1%, which is a good estimation for this kind of storage. Furthermore, we have input and output temperature differences and pumping parasitics needed to operate the storage. The storage is also minimal content, which means that one cannot use every cubic meter of molten salt of the storage inventory, but both tanks have to have minimum molten storage inventory, which cannot be used for discharging. The power block has been already loaded. In this case, the 50 megawatt standard power block of Greenius has been used. This one has a wet cooling tower. It generates 50 megawatt cross generator output, has a maximum load of 100%, and the condenser pressure is about 80 millibar. So now all interesting technical informations are given. The only thing which is left is the economics. If we go to Economics tab, we can inspect the values which are used here. In Greenius, we have 4 main input data for specific costs. One is the non-conventional components. In this case, this means solar field and auxiliaries. We have conventional components, which means power block and balance of plant. and we have the storage. Finally, we have to use land costs, since the parabolic trough plant needs a large area of land to be erected. Then we have a second option to define the timing of the plant. This is the reference year of discounting, the first operation year and the construction period, and we can also define methods of depreciation. The last input window of the economics is the financing window. Here we can choose different financing sources and different parts of debt or equity funding. In this case, it's a typical 70% debt funding, and the debt financing is drawn from one institute, so the share is 100%. Interest rate is given here, as well as debt term and other financing parameters. After the definition of all these data, we can start the simulation itself. This can be done by either using the menu project case and run calculation, or just by pressing the F9 tab. This was a simulation of a whole year, which is done in a few seconds. After that, we can go to the inspection of the results. The results window is subdivided into 3 further windows. One is the typical operation year. By clicking the Edit button, we can open it and maximize it, for example. Here we have a lot of technical information and simulation results. And it's again, we have 4 different tabs. We can look at months, weeks, days, and hourly results. From this table, many input information is available, as well as calculated results. On the left-hand side, all these values are explained further. But Greenius offers also the option to have a graphical representation of the results. To do this, we have to switch to View Graph and choose some of these results. For example, the D&I collector area, solar heat used for steam, and the gross electrical output. Then we have to press Refresh Graph, and we can see the monthly values in this case. We can also switch to weekly datasets, again Refresh Graph, and have weekly results. So the red line is the gross electrical output, the green line is the solar field output, and the orange line is D&I times aperture area. We can go further and inspect daily values, and finally also hourly values. It's also possible to modify the display period to look into single days. Another option here is to export the simulation results via Save Active Table As. And here you should typically choose Excel format, and then you are able to save or export these data tables to your computer and to your hard disk in an Excel format, which can be processed further with Microsoft Excel. The second output window is the cash flow window, where a lot of information about the economical simulation is given. You can look into the summary. And here we can see total revenues for the whole lifetime of the plant, as well as financing costs, debt service, and a couple of more economical outputs. And the third result form are the key results. In this case, we have again 2 main informations. One are the key technology results, and the second one are key economical results. Key technology results contain information about meteor data, site position and orientation, as well as system dimensions and major simulation results. Key economic results contain the financial input parameters, as well as simulation results of the financial model. This was the first exercise for Greenius to show how to use the software for a parabolic trough concentrating solar power plant. If you want to stop the Greenius and you have done any modifications either in a project file or in some of the unit files, Greenius is typically asking you if you want to save any of your changes, and you can either save all, no, or none of them before closing the software. In exercise 2, we are talking about the sizing of the solar field and how Greenius can be used to find an optimal solar field size. In principle, there are several possible solutions to find this optimal solar field size. But my recommendation is, first you have to fix the site itself and you have a relevant meteor file. Then you have to fix the power block size and all specific cost parameters. You should use a reference DNI of about 750 watt per square meter and find a solar field size suitable for the power block nominal input. After that, you may do several simulation runs varying the solar field size systematically around the value found under point 3. Afterwards, you make a table with the levelized electricity costs and the solar field size in order to find the cost optimal solar field size. We will again start the software Greenius. And in this case, we can use already edited project, the last one. And this makes it easier to make new simulation or modify projects, since all informations, all input we have modified in the first example is now available here. We have the location, the meteor data file, as well as the solar collector, solar field layout, and the thermal storage type. Again, start the simulation by pressing F9. We will get the result, and we will get the total net electricity generation here, 207,064 megawatt hours, and we get a levelized electricity cost shown here of 0.1245 euro per kilowatt hour. The next step is to write these numbers down and modify the solar field. We go from 156 rows to 150 rows. Run the simulation again and get a new number for electricity generation, 200,645 megawatt hours, and levelized electricity costs of 0.1249 euro per kilowatt hours. This could be done also for 162, 168 loops, and then we get finally to a table like this one. Here, given the number of loops, the relevant aperture area for this number of loops, the net electrical output, and the levelized electricity costs. Here, the levelized electricity costs for 156 or 162 loops are the least values. This is another example of finding an optimal solar field size. Here are two different sites plotted. One is Daggett in blue in California, and the next one is Seville in Spain. The main difference between both sites is the annual DNI. In Daggett, we have 2,790 kilowatt hours per square meter. In Seville, we have 1,837 kilowatt hours per square meter, annual DNI. The nominal power block heat input for both plants was the same. If we use a reference DNI as proposed of 750 watt per square meter, we will come out at 235,000 square meter for Daggett and 275,000 square meter for Seville, shown here as minimum for the LSC values calculated for both sides. The reason for this behavior is if you increase the solar field size, you get, of course, more output from your plant. This is going to reduce your levelized electricity costs, but if you increase the solar field size further, you will get more dumping, since once a certain point is reached, the output will only be increased by a small extent, but the costs will be increased by a larger extent, since the power block is running at full load and the storage is fully charged for many hours. So this is exercise 3. Similar to the solar field size, we can also vary the storage size and find an optimal storage size with the levelized electricity costs. Here again, you should start with the NMENA 1 configuration and vary the storage size from 0 to 12 full load hours in steps of 3 hours. This is again the configuration we had before. The thermal storage has 940 megawatt hours. That means 7.3 full load hours. So we start with 0 storage. In this case, you may realize that Greenius changes the display of this capacity to a red number. This is just a warning for the user that the value is out of the expected boundaries in this case. Nevertheless, you can do simulations with this number. It's just a warning. Again, we can do this start the simulation by the run calculation and get a total electricity generation of 142 gigawatt hours and levelized electricity costs of 18.12 euro cent per kilowatt hour. We write down these values in our table and change this storage capacity to 390 megawatt hours. That means 3 full load hours. Do the simulation and get the electricity generation of 180 megawatt hours per year and levelized electricity cost of 0.143 euros per kilowatt hour. This can be repeated several times in order to get the full table. I have prepared the table and it's shown here. So the capacity of the storage is varied from 0 to 12 full load hours, and the levelized electricity goes down to a certain point, and the storage capacity of 9 hours, the lowest levelized electricity cost for this configuration. We can also realize that the dumping goes down considerably. Dumping means that a certain amount of total heat, which can be in general generated by the solar field, cannot be used by the power block or the storage, because the power block is running in full load and the storage is totally charged, for example. If we're talking about a cost optimization of solar field size and storage size, we have also to consider the impact of the specific costs on the levelized electricity costs. In this exercise, we will vary the specific storage costs from 35 over 45 to 55 euro per kilowatt hour. And we're gonna watch the impact of these modified specific storage costs on the levelized electricity costs. Again, we start with the Enamina 1 configuration. Open this project, load all relevant data into Greenius, and we'll go to vary the storage cost. There are two options to modify storage costs. One is on the costs input sheet. We can use this button with the arrow to modify specific costs. Or the second option is to go to the Technology tab, open the storage input window and use the costs menu to get to the same input window for specific costs. So this is the first figure, 35 euro per kilowatt hours. We leave it as it is and run the simulation. We get again the well-known 12.45 euro cent per kilowatt hours. And we change the storage costs to 45 euros per kilowatt hour, accepted by pushing the OK button and run the simulation. We get now 12.85 euro cent per kilowatt hours. Again, I have prepared the table in advance. And here we can see the impact of specific costs on levelized electricity costs. The net electrical output is not changed since we have not modified any technical parameters, just financial parameters. So the fifth and final exercise gives some more information about meteorological data sets which are used in Greenius. So Greenius itself comes with some meteorological data set, but normally you are going to simulate your plant at a site for which Greenius does not provide meteorological data set. So there are several sources where you can acquire such sets. For many sites in the US, there are typical meteorological years available from the web for free. For European sites, there is a website which is called Satellite, and also there you can get a couple of data sets for European sites. Another option is also to use meteorological data sets from Meteornorm. This is software which you can get also from the supplier for about 500 or 600 euros. Meteornorm can provide typical meteorological data sets for many sites over the Earth, and this can be used for a first simulation or for studies. Furthermore, you may have ground measurements for a specific site or satellite data from commercial suppliers like Solemi. So Greenius gives a lot of import filters for this kind of data sets. If you go to the project site and the Meteo input window, you can push the load button, and typically if you push the load button, Greenius shows you the meteorological data sets which are in the relevant repository. All these data sets shown here are of the Greenius ASCII format. This is shown by the extension GPA. But you can also modify this, for example GPD, which means Greenius digital data file, which is a binary format. Then you may see other input files which can be loaded. Other import filters are for NREL TMY3, which is a comma-separated values format, or the older NREL TMY2 datasets. Also, an option is to load satellite irradiance datasets, which are actually tabulator separated values. In this case, you can choose the dataset and open it, and for this satellite irradiance datasets, you have the option to choose between different years. For example, 1998, and load it into your Greenius. And again, we get the warning that the meteor site is far away from the project site, and Greenius offers the option to copy the meteorological dataset coordinates to the project site coordinates. The meteorological data window in Greenius may also be used to check the right definition of your time zone and the correct definition of the first hour and so on. For example, you can choose to view the daily plot window and plot into this daily plot window, for example, direct normal irradiance together with the sun elevation, which gives you an important hint whether both values are matching. This is particularly correct for days with good irradiation conditions. So these arrows can be used to switch from one day to the next, here for January. And in this case, you should check whether the sunrise and sunset conditions are matching your DNI values. If there is, for example, something wrong with your time zone definition, so if your dataset has a wrong time zone definition, let's say -1 instead of +1, then you will see that there is a certain gap or set off between the sun position or sun elevation and the DNI data sets. You will have hours where the sun is above the horizon, but no DNI is there, even for good days or days with almost perfect irradiance conditions. On the other hand, afternoon you have hours DNI values, but Greenius says, okay, the sun position is below the horizon. If you start the simulation with this kind of data set, you will get wrong results. If we switch back to the data table, then situation may occur that you have measured irradiance data for a specific site, and due to any reason, some of the data are missing for certain hours. Greenius needs a full data set, that means 8,760 hours per year, and if some hours are missing, you run in trouble for the simulation. In order to modify your data set, you have several options. You can either just copy the hour before or the hour after the certain hour where the data is missing, or you use a kind of interpolation for that missing hour. So this was the last exercise of this Anamenia video tutorial blog, and I want to thank you for your attention.